calculated responses of these single degree of freedom oscillators. Typically, civil structures are multi-degree of freedom, but for our purposes, we broke it down to single degree of freedom, and then you can recombine it afterwards. It's very complex to go through with the multi-degree of freedom. So basically, they're subjected to these forcing functions from things like earthquakes, explosions, wind loads, things of that nature. So basically what we have here, this is previous work done by my advisor here, and he has a function. This was an earthquake in Los Angeles in 1994, and this is the time versus the ground acceleration. Initially, he had here the linear interpolation of the function. He had discrete data, and then basically he improved upon that by using a cubic spline interpolation, which basically what he has is there's individual points, and between each point it was approximated, so there is a cubic polynomial between each point. So there's multiple functions for this. Now, through successive integrations, you're able to get this, which is basically frequency versus the acceleration. Now, what this tells you, the maximum acceleration that an oscillator, part of the building, is going to experience when it's subjected to an earthquake like this. That's basically the point of this. Now, you can adjust the stiffness to change, and to change the reaction to see how that works, or add damping, which is what slows the acceleration of the oscillator. So basically, that was the point of this part here. Now, what we had planned to do with my part of the research, we had planned on, because this is a bunch of different functions, we wanted to use one function to control all the oscillators, because each point on here, that's a bunch of different oscillators. With one function, you can control using this Chebyshev approximation, which is what we used over here. You can control all of them. You can change the stiffness, add damping, just by manipulating the coefficients. Now, we went with an easier function, which is an explosion. This is a mine blast that was taken at a potential refuge shelter 3 miles away from where the explosion was. And so basically we got this discrete data, and we did the same thing, a cubic spline interpolation, and that's how we got this data here. We initially started with the least squares approximation, and we started just for comparison purposes to a polynomial to the second degree and seventh, and once we got up to 21st, it became apparent we were getting numerical problems. This wasn't going to be adequate to approximate our function. So that's when we went with these Chebyshev polynomials, which there's a recursive function to generate them. They start at 0, they go the whole way up to infinity. From a graph of -1 to 1, they're orthogonal. So basically, if you have 1 to the 5th degree, it's going to cross the x-axis 5 times. So we used those to approximate our function here. Now, we had started using 5, and we got, it all landed on there, so we knew that that was going to work. But unfortunately, once we played around with it a lot, it took 256. The 256 degree is what we had for our function. Now, that's basically not reducing the complexity of the problem. So basically what we're planning on next is we're just working on more, simple graphs. This one's complex here because it has this plateau. At the beginning, it peaks, and then it just does a dip and then comes back down. That is what gave us the problem there. So we're working with smaller ones, because if it had, to the, the 4th degree or the 5th degree, basically you can control the whole function, you can take a derivative, and then you can calculate the max peak acceleration for each individual oscillator right there. So that's what we're working on right now. Unfortunately, with a complex function, it's really not saving you any time, and that's what we found out. More to prevent damage. It's more because you're going to know at what point of this building how fast that's going to accelerate when it's exposed to this type of a blast or this earthquake. So you can adjust. I mean, you can't change the mass, but you can change the stiffness of it. So basically to prevent the damage that would happen were this to happen again.